High-speed internet literally anywhere on Earth. I mean, think about it. The top of a mountain, the middle of the ocean, or maybe just your family's place way out in the country. That is the incredible promise of Starlink. But how does it actually pull it off? Let's get into it.
So yeah, how does SpaceX do this? How are they beaming fast, reliable internet from space all the way down to a little dish on the ground? Well, that's the big question we're going to break down right here.
You know, the entire secret to Starlink, the one thing that makes this whole system even possible, really just boils down to one simple concept: getting closer. And to understand what that means, we need to talk about orbits.
Starlink operates in what's called low Earth orbit, or LEO for short. Now this means its satellites are incredibly close to us, well, relatively speaking. And this proximity, this is the absolute key to the entire system's performance.
Okay, so using low Earth orbit creates this fundamental trade-off. On one hand, being so much closer means the signal has way less distance to travel. That gives you lower latency, that super fast response time, and a much stronger signal. But here's the catch. A single LEO satellite can only see a tiny patch of the Earth at any one time. So to get that continuous global coverage, you need a lot of them, a giant constellation of thousands of satellites all working together.
Right, so we've got this massive constellation of satellites, but what are the actual physical parts that make up the Starlink network? It really breaks down into three main components.
First up, you have the space segment. This is the backbone of the whole network. This massive fleet of small, advanced satellites that are just blanketing the globe in low Earth orbit. You can basically think of them as flying internet routers up in the sky.
Second is the part you'd actually see at your house or on a boat, the user terminal, or dishy, as a lot of people call it. But listen, this is not your parents' old TV satellite dish. This thing has a super sophisticated phased array antenna inside that can electronically steer its beam to lock onto and track these fast-moving satellites as they fly across the sky, all without physically moving an inch. It's pretty amazing.
And finally, the third piece of the puzzle, the ground stations. These are the absolutely crucial link back down to Earth. They act as gateways, connecting the satellite constellation to the existing fiber optic internet backbone that, powers the web as we know it. Okay, so we've got the three main parts: satellites, dishes, and ground stations. But how do they all work together? To really see that, let's just follow a single request for data. Let's say you clicking on a video and see the journey it takes through the whole system.
It all starts the moment your computer or your phone sends a request to the Starlink dish. The dish then uses a really cool tech called beamforming, which is kind of like an electronic spotlight for data, to create a super focused radio signal and shoot it right up to the satellite passing overhead. That satellite then instantly relays your request back down to the nearest ground station, which plugs it into the global internet, and the data you wanted, it comes all the way back along that same path in reverse, all in just a fraction of a second.
But what happens if you're in the middle of the ocean, like hundreds of miles from any ground station? Well, that's where the next evolution of the system comes in. The newer Starlink satellites can actually talk to each other using lasers. Yeah, lasers in space. These inter-satellite links mean your data can hop from satellite to satellite in orbit before it comes back down to Earth. It's just perfect for providing service over oceans or the polar regions. Now, to really appreciate what makes Starlink such a huge leap forward, it really helps to compare it directly with traditional satellite internet. And the difference, once again, is all about the orbit. So traditional satellite internet uses what are called geostationary or GEO satellites. And the difference in altitude here is just staggering. That massive distance for the GEO satellites creates a really significant signal delay. We call that latency. And it makes things like online gaming or even video calls pretty much impossible. Starlink's LEO orbit just drastically slashes that travel time. The result is a connection that feels less like old-school satellite and a lot more like modern fiber. Just try to wrap your head around this. A traditional GEO satellite is 36,000 kilometers away. That is a massive, massive distance for your data to have to travel.
By contrast, a typical Starlink satellite is only about 550 kilometers up. Your data travels about 65 times less distance. So, here's the bottom line. That is the fundamental reason Starlink can be so much faster and more responsive.
So we get the how, but what about the so what? Let's zoom out for a second and look at the real-world implications and also the really serious engineering hurdles that come with building a system this ambitious.
And trust me, this stuff is not easy.
You have to precisely manage and deconflict thousands of satellites, all moving at 17,000 miles per hour. You've got to avoid radio interference, manage the limited power on each satellite, and seamlessly hand over your connection from one satellite to the next as they fly by, all without you ever noticing a single glitch. It's a massive software and hardware challenge.
But the payoff is already becoming super clear. Its biggest impact so far is in bringing real broadband to underserved rural and remote areas. But it's also proving to be a game changer for industries on the move, like shipping and aviation. And it's been absolutely vital for emergency communications in disaster zones where all the ground infrastructure has been destroyed.
So if you remember anything from this explainer, remember this. Starlink's magic really comes from its huge constellation of satellites in low Earth orbit. That low altitude is what unlocks the low latency, high-speed performance. It's this incredibly complex fusion of advanced radio, wireless, and satellite engineering that is truly redefining what it means to have global internet access.
And that kind of leaves us with one final thought. We've spent decades wiring up our cities and our towns, but a system like this promises to connect basically everyone else. So the real question is, what actually changes when every last remote corner of our world finally comes online?